right, honing some chill vibes here. All right, chapter 10. We're doing it. Of course, I could sit here and listen to this chill music all day, but it's time to get it going. There we go. Let's turn that off. Okie dokie. I was getting a little trouble on my Wi-Fi there. Let's get it going, folks. So I split up this chapter into two parts, valence bond theory and molecular orbital theory. And I wanted to get these lecture notes out to you. So for now, I've just got these slides made up here for valence bond theory. And I'll have another set of slides for molecular orbital theory. And what I also want to do is kind of go through some of the historical context in how molecular structure was come up with. There's some really cool and rich, interesting history. I'm not going to quiz you on dates and names and stuff like that. I just wanted to go through a little bit of this because I find it really interesting. So first, we'll start with valence bond theory. So valence bond theory is it's really the original description of molecules via quantum mechanics, okay, which is very cool. And so in 1916, and so this is like before most of quantum mechanics was even worked out. So in 1916 at the time, Schrodinger and a whole bunch of other people were still grinding things out and trying to work out just quantum mechanics to describe electrons and protons, let alone describing molecules. So, but famously in 1916, Lewis himself, right, of Lewis structure, at UC Berkeley, proposed that a chemical bond forms from the interaction of two bonding electrons. So this is a hugely famous result, right? Because as we know, it's two electrons paired up that make a chemical bond. And he worked this out 10 years before Schrodinger worked out his equation. So then in 1927, Heitler and London, and so that is the London from London dispersion forces. So all of these are big, huge names. So Heitler-London theory was formulated. So Heitler was able to use Schrodinger's equation in 1926, so just literally 1 year later, and he was able to show how two single hydrogen atom wave functions could be joined together to form a covalent bond and an antibond, okay? And so the story goes that Heitler and London worked out these details overnight upon reading Schrodinger's paper. So like instantly they were like, this is a hit. We can do this. Let's make up chemical bonds. Okay. So then 2 years later, between the years 1928 through 1930, Pauling, the Linus Pauling, right, at Caltech, whom we've already talked about, used Lewis, Heitler, and London's work to establish resonance and orbital hybridization. And by 1931, Lewis published his landmark book on the nature of chemical bonds. And I forgot to bring this home with me. I have a copy of this book in my office. It's really cool if you're interested in the history of science. So it's really amazing when you think about all these years. This stuff was just happening like that. And they didn't have any computers to work through this stuff. They didn't have Mathematica. They didn't have Spartan or Gaussian. So it's amazing to me that they could work through this. So I just want you to kind of recognize some of these names is all, the point of this. And so then molecular orbital theory, so that's going to be the subject of what's coming in the next week, week 11. But just to briefly touch on this, molecular orbital theory is the modern approach for quantum computation and molecular orbitals. So it's built on valence bond theory. And then here we go, more famous names. Hund from Hund's rule. Mulliken from the Mulliken oil drop experiment. Slater, like the Slater determinant. Leonard-Jones, the Leonard-Jones potential well. And Huckel, the guy who worked out aromaticity. All of these folks built MO theory in the immediate years after 1927. Okay, and they did this as a collaborative effort. Amazing. So the first quantitative use of MO theory came from Leonard Jones in 1929. And they were the first, or excuse me, Leonard Jones is one person. It's a hyphenated name. So they were the first to predict a triplet ground state for diatomic oxygen. So remember, triplet, two unpaired electrons. And so that's for O2, right? For diatomic oxygen, that's O2. And we know O2 to be a triplet ground state. In other words, it has paramagnetism. Okay. And so then eventually Huckel applied MO theory to describe conjugation and pi bonding and aromaticity in organic molecules in 1931. And today, nearly all modern computation relies on some form of MO theory. So again, really, really cool history. You don't have to memorize this, but having some familiarity with the names and what the folks worked on, that's